Okay, so the second part here of graph theory, section 4, is the famous traveling salesman problem. So here we have approximate geographical representation of what do we got here? 5 cities, 6 cities, 6 cities in the U.S. And there's a weighted graph, right? There's mileage. That's the numbers on the edges. And the idea here is like, traveling salesman, you want to visit all of these cities, but you don't want to, obviously cost is an issue, right? It costs money to fly and or drive out to these cities. So you want to visit each city exactly once, except where you start, in the fewest miles. Okay, that's the question. So this one really not a problem about getting everywhere, right? There's roads that connect all of these cities to each other. That's not the issue. The issue is doing it with the fewest number of miles. And so that's the traveling salesman problem. And we take a look here. Here's a basic chart of that graph. Has the cities, the 6 cities and the mileages between them. And here we're asking about what's called a Hamiltonian cycle. So a cycle in a graph G that contains each vertex except the starting vertex exactly once is called a Hamiltonian cycle. Right? So do we have a Hamiltonian cycle here, for example, 16, right? Again, it's a cycle that contains each vertex exactly once. So take a look at that and see if that happens. Again, you don't have to hit every edge once, just the vertices. So again, back to the traveling salesman problem. Unfortunately, there is no, other than brute force, which means do every single possible combination, which with 6 cities is annoying, with 15 cities is tremendous number of things. Almost impossible even for a very powerful computer to do it in any kind of timely fashion. That's the only way to figure this out for sure. But we do have some approximation methods, as always, right? And so the first one I believe is called cheapest link, yes. So the cheapest link method is pretty much what it says, right? You start with the shortest path, the lowest weight, and then you just keep adding the next shortest ones as long as you don't create a vertex that gets degree 3, and then you just keep going until you have a cycle, right? So from our original problem, right, I mean, I'll go through it there, but clearly the lowest number in this is what, 2 is Boston to New York, right? So you'd start with that leg there, and you'd fill that in, and then you go to the next one, and you continue to do that unless you do degree 3 or complete the cycle early. So if you were to go through the cheapest length, right, first we have New York to Boston, that's 216, then DC to New York is 228, Cleveland to Chicago, DC to Cleveland. Then the next number on the list would be Boston to DC, but there's a reason we can't choose that, right? Why can't we? So, right, must violate one of those 2 things, complete the cycle earlier, create a degree 3 vertex. Then 462, also a no-go, and then it looks like you finally need KC to Boston, and then that gives us our number. Okay, so that's one approximation method for the traveling salesman problem. Pretty straightforward. Here's a couple of neat things too, bringing in 254. We can represent graphs a couple different ways with matrices. So one representation is called an adjacency matrix. So you select any ordering of the vertices, it doesn't really matter. Label the rows and columns with those ordered vertices, and then the entry in row I, column J, I not equal to J, is the number of edges incident on I and J, and if I and J are the same, it's twice the number of loops. Okay, so let's shrink this down so we can see it. Let's create an adjacency matrix here. So I've ordered this graph A, B, C, D, and E. So A to A obviously is 0. A to B, there's 1 path from A to B, right? So again, it's the number of edges incident to the 2. So there's 1 edge incident to A and B. A and C has no edges. That gets a 0. A and D has an edge. A and E has no edges. Okay, and so you follow that through. If there's an edge incident, you put a 1. Otherwise, it gets a 0. Okay. And in a simple graph, right, it has to be simple. If you take a look at a squared, a cubed, a to the 4th, you actually get the number of paths of varying lengths. What do I mean by that? Well, here's our adjacency matrix for this particular graph here. So let's take a look at a squared. Okay, so all you do is take this matrix here and square it, right? It's a square matrix, so it's not a problem. You get these particular values here. Now take a look. In row A, column C, the entry is 2, right? So because it's a squared, those are paths of length 2. So there has to be two paths of length 2 from A to C. So are there two paths of length 2 from A to C? Yeah, there's 1, 2, and there's 1, 2, there's the other one. So yeah, there is. So it's kind of neat. A to the 4th, right? Same situation, same matrix, same graph. Row D, column E, we have our 5. This means there must be 5 paths of length 4 from D to E. 5 paths of length 4 from D to E. So here we're talking about D to E. And a length 4, right? 1, 2, 3, 4. That's 1. 1. You can go up. 2, 3, 4 is another one. You can kind of go through and verify this and play around with it, and there will actually be 5 of them. So that's kind of an interesting thing that comes out of that. Another type of matrix associated with a graph is called an incidence matrix. So this one's a little different. You label the rows with the vertices, and the columns are the edges. So you have to label everything here, edges and vertices. And the entry for row V column E is 1 if E is incident to V, otherwise it's 0. Okay. So again, same situation. I've kept the same ordering of the vertices. I've just now labeled the edges. And again, we'll shrink this so it's all the same frame here. You know, you take a look at the incidence matrix, right? Is A, there's a 1 there, so A and E1, are they incident? Yeah, they are. A and E5 is also incident, right? A is not, that vertex not incident to any of the other edges. So it turns out here, like it says, the sum of the rows is the degree of the vertex. Okay, so it's kind of an interesting representation of a graph. Now we're going to talk about another kind of graph called a tree. So let's go through some definitions. First of all, a forest is a graph with no cycles, not one. Okay, so a forest is a graph with no cycles. A tree is a graph with no cycles that's connected. So basically a tree is a connected forest. And the vertices are sometimes referred to as leaves, the vertices of degree 1. Okay. So this is an example of a tree. Okay, think about what it is. I mean, you're talking about minimum representation here in terms of edges, right? So this is useful if you want to, let's say, set up a sprinkler system in your lawn, right? It costs money to run pipe to all the different spots, so you want to be able to cover all these spots and run the minimum amount of pipe. So a bridge is an edge in a connected graph such that removal of that bridge makes it disconnected. So if we go back here, which, in this particular example, are any edges bridges? Well, yeah, actually, all of them, right? If you pull any edge from here, you're going to create components that will no longer be connected. So that's where this kind of Theorem 7 comes from. So T is a graph with n vertices. It's not surprisingly a T for tree. So if we have a graph on n vertices, the following are all equivalent. They're either all true or all false. So T is a tree, no cycles, n-1 edges, connected with n-1 edges rather, connected, each edge is a bridge. Any additional edge will create a cycle, and any two vertices are connected exactly by one path. Okay? And so a tree is a spanning tree of a graph G if T is a subgraph that contains all the vertices. And again, right, why are spanning trees so practical? You know, they're great anytime you want to be efficient with anything, whether it's cost, whether it's electrical resistance, whatever you want to think of. Spanning trees are kind of minimum coverage kind of situations. So they're definitely cost effective. So find all the spanning trees of the graph G, right? So again, we have to have the, remember it's a subgraph that has to have all the vertices. So it's a spanning tree, and it's a so we have to have all 4 of these vertices, and there are options, right? So this is one option. Are there other options? Of course, right? This is another option, etc. So a graph G has a spanning tree if and only if it's connected, right? So that's, again, a two-way street. So if G has a spanning tree, it has to be connected. If G is connected, it has to have a spanning tree. And so in a weighted graph, a minimal spanning tree is a spanning tree with a minimum weight. similar to the traveling salesman problem a little bit. So given this particular example, we're going to call this Kruskal's algorithm to find the minimum spanning tree. So you start with, of course, you need all the vertices, and you just, at each step, add the edge of minimum weight that doesn't make a cycle. And as soon as you get to n-1, you stop. So it's very similar to the cheapest link method in the traveling salesman problem. So from the previous example, right, we have to have all of those vertices, A, B, C, D, E, and F. This is the first one, so we add that, right? Then there's the 2. If that doesn't create a cycle, we add that. So those are going to be in here, right? The 1 and the 2. And then again, you continually add until you get the minimum spanning tree. This one has, of course, weight 12. You just add them up. So here we're finding another spanning tree as part of that worksheet, or you are. Again, another minimal spanning tree. You're going to use Kruskal's algorithm there. And those are the only 2 problems for section 4.